In the video for exercise 718, we talked about how an SN2 reaction is pretty straightforward. You always have just nucleophilic attack and loss of a leaving group happening at the same time. But the mechanism for an SN1 reaction can be much more complicated. You still have those two standard steps always. Loss of a leaving group happens first and then nucleophilic attack. But because you form a carbocation in an SN1 reaction, you could have carbocation rearrangements, so always watch out for those after the leaving group leaves. In addition to that, you may have a proton transfer at the very beginning of the mechanism. That's if you have a bad leaving group. That's what we talked about in exercise 718. Now let's talk about when you would have a proton transfer at the end of an SN1 mechanism. You'll have a proton transfer at the end of an SN1 mechanism if the nucleophile has no charge. When the nucleophile has no charge, you'll need to do a proton transfer because after it attacks, some electrons that it had all for itself will be shared with a new bond to the electrophile, to the substrate. And so if it originally had a 0 charge, it will end up having a +1 charge, and you'll have to do a proton transfer to get rid of that +1 charge. So for example, let's say you had a carbocation and what would happen if you had water, for example? If water were going to attack that? Well, water has a 0 charge. It has 2 lone pairs all to itself. But if the electrons here were going to attack that electrophile, then one of those electrons, one of those lone pairs is now shared. So there isn't as much electron density around the oxygen, and if you calculate the formal charge, you'd see that the oxygen would have a positive formal charge. And so you'll have to do a proton transfer reaction to take a hydrogen off of your nucleophile in order to give it a 0 charge again. So another water molecule, for example, could come, steal that hydrogen. This is our proton transfer. Those electrons go onto the oxygen, and you end up with a neutral molecule. And then floating around somewhere, there's the H3O+. That we made here. So you could see how if you start out with a neutral nucleophile, a nucleophile that has no charge, it ends up with a positive charge after it attacks the electrophile. And so you have to do this proton transfer in order to give it back its 0 charge. Okay, so now we have this complete SN1 idea. Let's just do some practice recognizing when we would have to do this proton transfer at the end. So here are what some nucleophiles can look like. So let's say we have an SN1 process involving each of the following nucleophiles. Will they require a proton transfer at the end of the mechanism? Well, the real question is, does the nucleophile have a charge? Here, you have a metal and a non-metal. Anytime you have a metal, then you know you have a metal gives its electrons away to the more electronegative thing. So you usually have an ionic compound. So that NaSH is actually two little groups. The sodium, and when you put them into solution, they come apart. The sodium is a very big atom. Atoms get bigger as you go to the left, and as you go down, sodium is all the way on the left on the periodic table. So it's really big, so it's able to dilute that positive charge by spreading it out, and that just floats around in the solution. The SH minus, that's your nucleophile. Does your nucleophile have a charge? It does. So you have a charge, and so you would not need to do a proton transfer. At the end of the mechanism. In the next example, H2S, in this example you have two nonmetals. So you do not have a charge. So wait, this one has, you could say the nucleophile, and this top one, the nucleophile has a charge, so you would not need to do a proton transfer. In this molecule, we have two nonmetals, those are covalently bonded, so here the nucleophile does not have a charge. So you would need to do a proton transfer. At the end of the mechanism. Similarly here, water, there's no full charge there. You have two nonmetals, so there's no full negative charge on that nucleophile. And so you would say this nucleophile does not have a full charge, therefore you would need to do a proton transfer at the end of their mechanism for that one. For ETOH, ET is an ethyl group, so CH3CH2, and then ETOH is ethanol, drinking alcohol. And in that case, you have all nonmetals. All nonmetals, and so there is no full negative charge there. Because the nucleophile does not have a full charge, you would need to do a proton transfer at the end of the mechanism. Now in this example, this next example, we have a metal and nonmetals. So this is an ionic compound. So you have the sodium with a plus charge and the Cn with a minus charge. And it's just this that's your nucleophile. The sodium floats off in solution. So you'd say the nucleophile does have a full negative charge. So you would not need to do a proton transfer at the end of the mechanism. Now in this next one with table salt, if you were doing an SN1 reaction with table salt, notice you have a metal and a nonmetal. This is an ionic compound. And indeed, the word salt in chemistry really is just a synonym for an ionic compound. So there are hundreds of salts because there are hundreds of ionic compounds. So here, our nucleophile is the Cl-, the Na+ just floats off in solution. And so, because the nucleophile does have a full negative charge, you would not need to do a proton transfer at the end of the mechanism. In this next example, again, we have a metal and then nonmetals, so this is also going to be an ionic compound. This is Na+ and NH2-. And because the nucleophile does have a full negative charge, you would not need to do a proton transfer at the end of the mechanism. In H, you have only nonmetals. So this is a covalent compound, and the nucleophile does not have a full negative charge. So in this case, the nucleophile does not have a full negative charge. And so you would need to do a proton transfer at the end of the mechanism if this is your nucleophile. In this next case, we have a metal and nonmetals, so that's an ionic compound, so this is really Na+ and OMe-. Me is a methyl group, so that's really like a CH3. So in this case, the nucleophile does have a full negative charge. And because the nucleophile has a full negative charge, you would not need to do a proton transfer at the end of the mechanism. In this next example, we have a metal and nonmetals. And so this is really an ionic compound. We have Na+ and OET-. So the nucleophile does have a full negative charge. Because the nucleophile has a full negative charge, you would not need to do a proton transfer at the end of the mechanism. For K, remember Me is a methyl group, so this is really CH3OH. You have only nonmetals there. So that's a covalent compound, and there is no full negative charge in, there's no full negative charge in that compound. So because there's no full negative charge in that compound, which is methanol, you would need to do a proton transfer at the end of the mechanism if you had that as your nucleophile. Finally, in this last one, we have potassium and bromine. Potassium is a metal. It's in the same row as sodium, and so here, that's going to be an ionic compound. The bromine, with the full negative charge, that is going to be your nucleophile. So because the nucleophile does have a full negative charge, you would not need to do a proton transfer at the end of the mechanism if that were your nucleophile. So in general, as you can see in all of these examples, we are going to do this proton transfer at the end only when the nucleophile does not have a full negative charge. If the nucleophile does have a full negative charge, then we don't have to do that proton transfer. So hopefully that gives us some practice in recognizing when we have to do this step at the end.